All right, so today we're looking at 5.4 in your text, and we're looking at what the second derivative test means. Okay, so in the notes that you see on the board here, as you write this down, I'll just explain what's happening here. So when we're talking about this second derivative test, obviously it's going to be tested. We're going to be testing something, right? This is going to be a test for something, and we're going to use the second derivative. So the question is, what can the second derivative help us to determine? Well, from our work in 5.3, previous section, we know that the second derivative tells us whether an interval will be concave up or concave down, right? We just got finished doing that. So the second derivative so far is telling us about the concavity of the graph. So SDT is how I'm just abbreviating, second derivative test. And when we use the second derivative test, it allows us to determine local maximum or minimums. And here's the key. Here's the shortcut part, without having to use sign analysis. So if you recall, sign analysis is where we take the factors of a function, or in this case, what we used to do to find max and min was take the derivative of what would be, the factors of the derivative. So here's the derivative down here. The factors are x and x plus 2. And so in sign analysis, you list the factors on the side here. And then you make a little elongated L. And for each factor, you place a 0 on the number line, which would be this bottom line. And you place a 0 there. And you know that for this particular factor, any value that's less than 0 would cause this factor to be negative and positive, right? And so we place the 0 across from each factor, and then we label the region whether it's going to be positive or negative, depending on the values that correspond to the number line. So sign analysis would then be an easy way, if we had multiple factors, an easy way to find out if this derivative, in this case it's when these two are multiplied together, so a negative value in this region, or in this interval, times another negative value would give a positive value for every x in this interval, right? We have a 0 here. For this one, we'd have negative. Negative times a positive, negative. 0, and then positive times a positive would be positive. So we're able to determine where the derivative is positive and negative and so on. Now, in connecting this with local max or minimums, what we took a look at was, where did the sign change from positive to negative, right? Now, positive derivatives look like this. A 0 derivative looks like this. Negative derivatives start to look like this. And so what does that look like if there was a graph underneath there? That looks like we are looking at a local maximum. And so we had determined before, using sign analysis, that this points us to a local maximum at x equals negative 2. And over here, conversely, we have negative values, right, for the derivative. And then we have a 0 value right here at 0. And then they start to be positive again. And so this, of course, looks like a local minimum. And if this is the derivative, this is the actual kind of parent function. Now I'll show you how to do this. It's called finding the antiderivative. And I'll show you how to do this a little bit later. But this is what the function would look like, because if we took the derivative of this, bring the 3 down, that's 1x squared. 1x squared, which when you multiply this out, you have x squared, right? And then over here, 2x to the power of 1. And so this x times 2 would be 2x. So that's what this parent function is, okay? Now, if I graph this out, which I did on the graphing calculator over here, turn that on. And here it is right here. That is this function right here. And so you see how our sign analysis pointed us to a local max at x equals negative 2, which looks about right. And a local minimum at x equals 0, which looks about right according to the graph. Okay? So you're with me so far on this brief review of sign analysis? Okay. Now, if we go back to this right down here, and this right down here, I'll just kind of get rid of this for now. Okay? At a local maximum, what do you notice about the shape of this graph, having in mind what we just learned about second derivative? How would you describe the graph in this, what I'm kind of pointing at right here? It's concave down. Thank you for noticing that. And so when we have a local max, immediately surrounding this, just before that point, just after that point, builds the graph that is concave down. That's very, very important. And over here, when we have a local minimum, that's because the graph immediately surrounding in that region there is concave up. Okay, that's very important. So here's the connection between a critical point, because the critical point would be this point in question, which comes from here and here, right? If I could find out what the graph is doing at that point, or what the concavity of the graph is at that point, that will tell me whether I have a local max or min. Okay? So let me just take, just because I'm just looking at your glassy eyes, so I think I need to just take one more minute on this, okay? But if I told you that we were concave up, let's talk about second derivative now. We were concave up here, and then we were concave down here, and concave up here. And I told you that there was a critical number here, a critical number here, and a critical number there, okay? C1, C2, C3. Now you have to wrap your head around it. It's almost like thinking in another dimension, okay? Don't think about the function right now. Don't even think about the derivative. Look at the second derivative here. If this is concave up, okay, in this region, concave up, and I have a critical number here, the concave up means that this critical number is automatically a local minimum. All right? Because now if you think of the first derivative, the derivatives are negative, negative, 0, positive, positive. That whole region is concave up. A critical number here. If it's concave down here, then this would represent a local max because it's got to be concave down. All right? Now, I won't continue on, but we have the same sort of thing. So the notes are now, right here, let's go. Okay. So this is, I'm going to go back to the steps in a second. We're ready for this now. Okay. So what we're saying is that if the second derivative evaluated at C, okay, so you have to know your critical numbers. And you say, okay, does this critical number now represent a local min or max? Before, we've done sign analysis or test points, right? We did test points on some of those optimization questions. You did test points. But now we can use the second derivative, yes?
Is it the C of the derivative or the...
Well, okay, so is it the C of the derivative or the original function? The C means critical number, okay? So the C is the x value that makes the first derivative 0. There is no other definition for C, no other values for C. C doesn't make any sense in the original function or in the second derivative. It only makes sense in the first derivative. So the only C that we're talking about is the x value or values that make the first derivative 0. So that's a long answer to your short question, but it's the critical number, it's C, it makes the first derivative 0. Yes? No. Critical numbers are not points of inflection. No. Very good question. They are different, okay? And if I just zip back to the notes here and we take a look at a graph, you see, that's a critical number, that's a point of inflection. That's a critical number, that's a point of inflection. So you're right, they are not the same. Good question. Any other questions like that? Yes. Yep. Points of inflections are always where the concavity changes. So that is where the second derivative, the sign of the second derivative, SIGN, where it changes. Okay. So from yesterday, look at this, second derivative. Okay. Sign analysis on the second derivative. Okay. The concavity is negative here, then it changes to positive. So this is an x value for the point of inflection. It's where the concavity, the sign, SIGN, of the second derivative changes from either negative to positive or positive to negative. So these are all representing points of inflection. And that was from the lesson yesterday. See that? So the points of inflection, the x values, okay, I guess not really described there, but anyways, yeah, they are where the concavity changes if you look at this from yesterday. Okay. Anything else? Okay, good clarification questions. Very good. All right, so we zip back down to here. This is the second derivative test, okay? So if the second derivative, when you plug your critical number in, if it shows up, like if that number that you have evaluated here, if it's a positive number, that means we have a concave up, and that means we have a local what? Careful, yes, minimum. Yeah. Concave up, you think, hey, up, max. No, no, no. If it's concave up, it looks like this, and so we have a minimum point. Very good. And of course, if the second derivative, when you evaluate it at a critical number and it shows up to be negative, then it's a local max. Okay. Now, if f double prime of c equals 0, what does that mean? F double prime of c. So the second derivative is 0. What does that mean again? The second derivative is 0. Yeah, it's a point of inflection. So it's actually not a critical number. That means you've messed up with your critical numbers, if that happens. So either you've messed up in your evaluation, or you've incorrectly determined a critical number if you have equals 0, because it shouldn't. The critical number should be only positive or negative. Okay. All right. So we'll do an example here, but I had these kind of notes ready for you. So this is sort of what you do. Okay. After you find the first derivative, then of course you find your critical numbers by setting that first derivative to 0 to find your critical numbers. Okay. Then, so if we're talking about steps here, step 2 would be to find the second derivative, and then evaluate, very important, find a number answer when you plug your critical number into second derivative. Okay, so if you're a steps person, then here are the steps. I kind of just went over this, but if you're a steps person and you like to see this, here you go. Find first derivative, find the critical number. Find the second derivative, plug c into that. Ask yourself, or find out if it's positive or negative. And then you can say, all right, if it's positive, I know I have a min. If it's negative, I have a local max. And this is at c. That's not me misspelling, etc. That's kind of fun. All right, so let's do an example here. This one says the function f of x is x cubed minus 12x plus 5. And the question would be, find local max, or minimum, okay, local max or minimum values using the second derivative test. Okay, so we're just going to follow those steps that you just wrote down. And we're not going to use sign analysis. Even if we really want to, we're not going to do it. We're going to find the second derivative, plug our critical value or values in. All right, so find the first derivative. Pretty easy. What's the derivative of x cubed? Just shout it out. 3x squared. Thank you. And then it's going to be minus what? 12. All right, and then plus 0, right? So just 3x squared minus 12 is the derivative of that cubic function. Okay, very good. What's next step? What does it say? Find c. Okay, so if we did 3x squared minus 12 equals 0, I'm going to have 3x squared equals 12, x squared equals 4, x is going to be equal plus or minus 2. Sound right? You guys? Okay, so plus or minus 2, those are our critical numbers. What's the next step? Next step is find second derivative, it's not? Okay. All right, so find second derivative. So f double prime of x is we're taking the derivative of the derivative. Okay. And so that's going to be